We're back at AP Free Response Review, and this is 2010 B, AB, BC Free Response 3. In 2010, Free Response 3 was a calculator problem, right? So back in 2010, 1, 2, and 3 were all calculators. So this is a calculator problem, which you can definitely see if you look at the solutions guideline because there's a lot of decimals. But just a heads up that in 2010, this was still a calculator section. So the figure above, this one, shows an above-ground swimming pool in the shape of a cylinder whose radius is 12 feet and whose height is 4 feet. So that's the height and radius of the actual pool, not the water in the pool. The pool contains 1,000 cubic feet of water at time t equals 0. During the time interval from 0 to 12 hours, water is pumped into the pool at a rate of p of t cubic feet per hour, right? So this is the rate that the water is going in. Right, this is water in feet cubed per hour, right? So just making a note that that's what that table is, water in. That's the rate, so it's the rate, right? The rate that the water is going in. The table gives selected values of P of T. During the same interval, water is leaking from the pool, right? So there is a rate out. Right? So this is a rate in and a rate out problem, and it might also involve related rates. Who knows? Good times. R of t is the rate out, and it is a 25 e to the negative 0.05 t. And then they do you a solid. They do tell you that the volume of a cylinder is pi r squared h, in case you didn't know that, which was nice of you, but also lends credence to my suggestion that there's a good chance that there might be related rates here. All right, cool. Couple things before we even start this. This is a classic rate in, rate out problem. There's going to be something asking you to relate these two rates in some way to find the amount of volume at a given time or the amount of water lost or whatever. The other thing to notice is that this is a table problem. We know what to look for in table problems. We know that two things come up a lot in table problems. Number one, we are sometimes asked to estimate the derivative of this quantity by using slope between 2 points on the table. The second thing is we are very often asked to integrate this quantity, which especially makes sense in this problem given that this is already a rate. So we're probably going to be asked to integrate this rate using some kind of area approximation method from the table. So LRAM, RRAM, MRAM, trapezoidal. It's very, very likely. Okay, so knowing that's what's coming up and also knowing that there's a good chance that there might be some related rates because they bothered to give me this, let's dig into this big problem. Part A. Use a midpoint Riemann sum, hey look, MRAM, with 3 subintervals of equal length to approximate the total amount of water that was being pumped into the pool during the window from 0 to 12 hours. Show the computation that leads to your answer. So, part A is exactly what we would expect from a table problem. What they want us to do is they want us to approximate the integral of P of t dt from 0 to 12. That's what they want, right? They want us to approximate this integral. Now, they said use a midpoint Riemann sum, and that's tricky because that means you need the middle of each interval. But they said use 3 subintervals. So the intervals from 0 to 4, from 4 to 8, and from 8 to 12. Those are my 3 equal subintervals, which means that my midpoint values are the values that occur in between. The y value at 2, the y value at 6, and the y value at 10 would all be the midpoint values. So this area is going to be the width of the first interval, which is 4, because the width of all the areas are 4, times the height of that first, that midpoint height in that first box, plus a 4 times the midpoint height in the next box from 4 to 8, the midpoint would be 6, plus a 4 times the midpoint height in this box, which is a 62. Now, it is a calculator section, so you are free to just type to get your answers, but you get that that's 660 feet cubed, right? And it's the total amount of water, which is why it's feet cubed. It also makes sense because you are integrating feet cubed per hour. So when you integrate, it's just feet cubed. You do need this, which is the logic of how you did it, and you need the answer with units. Part B. Calculate the total amount of water that leaked out of the pool during those 12 hours. Well, part B is going to be the integral from 0 to 12 of r of t dt, which is something you're going to make your calculator do, right? So you're going to put r of t in as your calculator y1 in all likelihood, right? So that's a 25 e to the negative 0.05 t, but you're going to use x because you're in function mode. Double check that everything's in right, okay? And then I'm going to integrate that. So I'm going to quit out, and I'm going to do math 9, which is function integrate. I'm going to go to vars over to y vars and pick y1 with respect to x from 0 to 12. All right, and when I do that, I should get something in the neighborhood of a 225.594. So that's 225.594 feet cubed. All right. Notice that you need that integrand again, right? You need the integrand that says what you're looking for, and you need your units, and your calculator's doing most of the heavy lifting. I'm going to suggest that there's a good chance that I might need this again. So I'm going to stow this. I'm going to store it as B only because it was my answer to part B. It doesn't have to be stored as B, but I'm going to hit stow and alpha B. And I'm going to always make a note on my paper of what I stored something as because I might need it again. So the reason I suggested that I might need it again is it's very, very common that they're going to ask you how much water is in the pool at the end of the window. Well, that's going to be however much you started with, plus however much you gained, minus however much you lost. So I'm probably going to need that number of how much I lost, which is why I stored it. Cool. Part C. Use the results from A and B, how nice of them, to approximate the volume of the water in the pool at time t equals 12 hours. Round your answer to the nearest cubic foot. Okay, so my part C then, right, the total amount at t equals 12, right, is going to be the amount that I started with plus the amount that I gain minus the amount that I lost, right? So it's going to be, I believe they said you started with 1,000 cubic feet, right, plus the 660 that you gained from answer A minus the... Oh, in fact, if you want, you can be a little bit safer and say, hey, I get that this is this integral, right? This integral minus this integral. And then you can just plug in your numbers, right? If you want to be super duper safe. So so that's going to be 1,000, right? So that's going to be 1,000 plus the 660 I got from A minus the thing I just stored as B. So I get 1434.405, right? So 1434.405 or 6, right? Feet cubed. But be careful because they specifically said round to the nearest whole cubic foot, right? Round to the nearest. So if I round this, and they did say round, that's 1434 feet cubed. That's the answer I have to give them. The AP wants you to round to 3 places or truncate to 3 after the decimal unless they expressly tell you otherwise, and here they expressly told you otherwise, so be careful. Cool. Finally, part D. Here come those related rates. Find the rate at which the volume of the water in the pool is increasing at time t equals 8 hours. How fast is the water level of the pool rising at t equals 8 hours? Indicate the units of measure. Okay, so how fast the volume is changing, right? So for part D, right? So the change in volume, right? The change in volume of the water, right, is going to be the rate in minus the rate out. That's going to be the net rate of change, right? So at t equals 8, that's going to be P of 8 minus R of 8. Well, I can find both of those. I know P of 8. P of 8 is a 60, and R of 8 is what happens if I plug in an 8 here, right? So I can find the rate of change of the volume of the water by essentially doing either a 60 minus whatever decimal I get if I want to find this value first, or honestly, I could just type this in, right? 60 minus 25 e to the negative 0.05 times 8 and hit enter. And I get that it's a 43.241 or 2, right, depending if you round or truncate. And because it's the rate of change of volume with respect to time, right, that's the volume's changing, that would be feet cubed per hour, right? So that's the first thing, right? This is the rate of change of the volume, right? So this is essentially the volume of the water. This is the rate of change of the water volume at t equals 8, right? That's what they wanted me to find. The second thing they said is, now that you know that, how fast is the water level of the pool rising? Well, now this is where it becomes a related rates problem, and this is where you need this. The trick here is that the R isn't actually an R. The R is a 12, because cylinders have a constant radius, right? So cones get skinnier as they get to the top or bottom, depending on whether it's a regular cone or an inverted cone. Oh, and for the record, I anticipate that I'm going to need this, so I'm going to store this as A. I didn't use A yet in this problem, so you can see I'm going to take Stowe, and I'm going to do alpha A, because I expect to need this again. Okay, so I'm going to keep in mind that 43.241, etc., and I'm going to give myself some space, because I need it. All right, so I know that here, although this is the generic formula for volume, for a cylinder, the height of the water is changing, right? The height of the water is changing, but the radius of the water is not changing. The radius of the water is a constant 12, because at the very bottom of the pool has a radius of 12, and as the water fills, the pool still has a radius of 12, because it's a cylinder, not a cone. So when I do related rates, I need a diagram and rates, which I kind of already have. Then I need an equation. Well, the equation that relates the volume here is volume of this cylinder is a 144 pi times h, because the radius is not a variable in this problem, it is a constant. I then derive my formula with respect to t, so dv dt equals 144 pi dh dt. And I found dv dt already. This was that 43.241 or 2. Right? That's what this was, approximately. And they want dh dt. So, essentially, my dh dt is just the dv dt that I just found divided by 144 pi. So my answer is that the height, dh dt, is changing at a rate of this number divided by, in parentheses, 144 pi. And I get 0.095 or 6, depending if you round or truncate, and height in this problem is measured in feet, and time has been measured in hours, I think? Yep. So feet per hour. And that's it. That's all they want.